Record. It's recording. All right. So now.
Boom. Yeah, looks good. All right.
So, if you guys got any questions, feel free to stop us. And we'll try to answer it to our best. All right. I'm Justin. The other
I'm
person
Kevin.
talking to me is my best friend Kevin.
Yeah, buddy. Dream team,
And
baby.
today we're gonna go over Diodes Workshop. So let's get into it. We're gonna. Damn, why isn't this working? All right. So the stuff we're gonna cover today is kind of the basics, but more into theory level of the basics. So we're gonna be covering semiconductors, the chemical bonding model, energy band model, doping, drift current, diffusion, PN junctions, biasing, what an ideal diode is, what's a real diode, Zener breakdown / avalanching, and some of the applications that diodes are used in. So a semiconductor is a type of material that's neither a good conductor nor a good insulator. It falls right in between. So its properties are between a metal and a non-metal. So the way this comes into play is that it acts as a non-metal, aka a insulator, when it's in normal temperatures such as room temperatures. And in EE330, if you take Ari, he'll tell you 25 degrees Celsius. So that's room temperature for a what's it called, for a semiconductor. And it acts as a metal, so anything above 25 degrees, so we'd be talking about 125 degrees in this range, or 300 Kelvin, and it'll act as a metal, so it would become a good conductor in that case, but that's only when the temperature increases. So with typical semiconductors, for electronic devices, we use silicon mainly just because it's more abundant, and some other ones that we use are germanium or gallium arsenide. And over here is our little model of a silicon crystal lattice, and that's basically what we use to kind of dissect semiconductor properties. So let's take a look at the chemical bonding model, Kev.
So basically, in the chemical bonding model, we got to start off with the foundation. So we have an atom. The atom has a nucleus and shells of electrons orbiting around that nucleus. As you can see, the outermost band would be considered the valence band. So the number of valence electrons that dictates the atom's tendency for chemical reactions. So for example, if one atom with only one valence electron comes into contact with another atom, and the other atom has 7 valence electrons, these elements are going to be highly reactive. And covalent bonds, they are the sharing of electrons between atoms. So again, another example is if one atom with 4 valence electrons comes into contact with four other atoms that also have 4 valence electrons, covalent bonds will begin to form between each of them. So each valence electron will pair up with exactly 1 valence electron from another atom. That's basically like the sum of it. So a hole is created, so when an electron breaks from a covalent bond, becoming a free electron. So when an electron breaks from a covalent bond, an electron hole pair is generated. And then an electron hole pair is recombined, so that's called electron hole pair recombination, when a free electron falls into a hole. So the generation and recombination of electron hole pairs can be caused from thermal energy. And the reason why is because this thermal energy will lead to an increase of kinetic energy in the valence electrons. So like the main takeaways for this is basically, you see that valence band, that's the outermost band. It has valence electrons. Covalent bonds, that happens when valence electrons from different atoms connect with each other. And free electrons basically are the ones that are, they've escaped that valence band, the outermost band. So now they're free electrons, they're just roaming out and about. And holes are basically once that valence electron leaves and becomes a free electron, it's going to leave behind a hole. And EHP, or electron hole pair recombination, is basically when a free electron finds a hole in another atom. And that will be it for the chemical bonding model. So the next thing will be the energy band model. I personally think that it's easier to understand what's going on. Basically, the chemical and energy band model, they're basically going over the same thing, just different parameters. So in the energy band model, the periodic table consists of 3 categories: metals, nonmetals, semi-metals. So metals are conductive, nonmetals are not conductive, and so that's why they're good insulators. And semi-metals have the capability to conduct electricity under certain conditions. Typically, these conditions depend on temperature. So the energy band model helps to better understand what conditions we need to be met in order for this semiconductor to be conductive. So as we talked about before, the valence band is the outermost shell of an atom that has electrons. So the conduction band is a shell outside of the valence band. So basically, when there's enough thermal energy, it will lead to excitation, and that electron would jump into that, what's it called? The conduction band. So the question is, so how much money is required to excite an electron to jump from the valence band to the conduction band? That is the band gap energy. And the band gap energy is the minimum energy required to excite an electron to break from its covalent bond. So as you can see in these pictures, the band gap energy in conductors, they overlap, or it's either very narrow. What that means is it's extremely easy for it to conduct electricity. You don't need a lot of energy for it to conduct electricity. The band gap energy of insulators, it's extremely wide, and also it can be referred to as forbidden gap, as you see in the picture. And the band gap energy of semiconductors is moderate. And that is why in engineering, we like to use semiconductors, because we can control those conditions. And that's basically the gist of the energy band model.
All right, so just to clarify, if you guys aren't truly understanding it, don't be scared or shy to ask questions, because we were like that the first couple of weeks with 330. We didn't expect to go into like chemistry, you know, to understand how a diode would work, but it turns out like this stuff is like really important. So yeah, don't really sweat it too much. There's a lot of videos on it. I mean, I had to watch a lot of videos to like truly understand this stuff, and now I'm comfortable with talking about it, and it's very interesting. So later on at the end of the workshop, we can probably recommend videos if you guys still need help understanding this stuff. And yeah.
YouTube.
Yeah, YouTube's everything. So now we're gonna get into doping, and this term called doping is basically when you add an impurity atom to the semiconductor. So in our case, we're gonna be working with silicon a lot. All right. So when we add an impurity, we're basically adding another element inside of our silicon crystal lattice. So here we got SB. I honestly don't know what SB is, but I know what B is. That's boron. So we're adding boron into our silicon lattice, causing an impurity. So this impurity will either lead to adding an acceptor, which is basically an extra electron, or we'll be creating a donor, which is a hole. So doping occurs when adding impurities into a semiconductor. Electron and hole densities in an intrinsic semiconductor is equal to one another. So therefore, doping creates free electrons or holes within semiconductors, thus turning this silicon lattice into an extrinsic semiconductor. So before, when it was just silicon all the way, silicon here, silicon here, silicon here, silicon here, silicon here, it was a pure silicon crystal lattice. So we would refer to it as an intrinsic semiconductor. Intrinsic, IN, and then you add the trinsic part at the end. But now, since we're adding SB and boron, it's becoming extrinsic, meaning it's got impurities in there, which will lead it to be more conductive. So adding, doping a silicon lattice increases the conductivity of the material. So when doping with more electrons, the semiconductor becomes considered an N-type semiconductor material. But when you got more holes in your semiconductor, the majority charge carriers are holes, we got what's known as a p-type semiconductor material.
So now we're going to be going into drift and diffusion. So basically the top picture you're going to see is drift. So drift occurs when an electric field causes charge carriers to move. So basically the electric field accelerates charge carriers to flow from one end to the other. But as you can see, it's kind of got this random pattern. So during this acceleration from one end to the other, these charge carriers are going to run into other atoms inside of that environment. So that's why there's that random pattern of movement. But even though that pattern of movement is randomized, the general path will still be generally in that one direction, aka to the other end. And next we have diffusion, and that's going to be the picture on the bottom. So basically diffusion occurs when a high concentration of molecules have a tendency to flow to lower regions of concentration, so referred to as the concentration gradient. So I'm going to use an example to explain this. It's like you imagine having a glass of water and you add in a droplet of ink into that glass of water. So that ink's gonna start to diffuse. But basically what it's doing is it's flowing from regions of high concentration to regions of low concentration. So that's the best analogy for diffusion.
All right, so now we're going to be talking about the p-n junction. So a p-n junction is formed when you got a fusion of p-type material being fused with n-type material. And this can happen a number of ways. The one that I prefer, well, that I know best, is called a liquid epitaxy. And that occurs when you have a solid substrate of, let's just say, p-type material. And on top of it, you kind of layer it with n-type, liquid n-type material. So you kind of apply it on top of the substrate, like if you were painting it per se. And since it's liquid, if you cool it down, it'll harden and it'll fuse together with the p-type. Later on, you'll learn that you can control the amount of, what's it called, liquid n-type that you'll add on to your substrate with adding something, I believe they're called barriers, not too sure, but they basically try to impose all of the n-type liquid going inside the substrate, the p-type substrate. So it kind of helps balance out the material itself. But anyways, so the p-type material, which is over here, this is the anode part. So the positive part of the p-n junction, and over here is the n-type material, and this is the cathode, which is the negative side of the material. And in the middle, we have something called the depletion region, and this is where we form. This is where you have your negative, your electrons moving across here, and you got your holes moving across here, thus forming an electric field in between. But we'll get to that when we get into drift again. So, diffusion occurs by having a majority of carriers from the p-type diffuse down to their n-type. So there's a large concentration of p-type on this side, right? Because it's a p-type material. So therefore, this p-type is going to try to diffuse down into the n-type, and the n-type is going to do the same thing. Large concentration of n-type over here, so a large concentration of electrons, and those electrons are going to diffuse down their gradient into the p-type material. And drift, in our case, would occur when this whole diffusion process is going on, and we got these ions meeting in the depletion region, right? So this will induce an electric field, thus causing drift to occur. And we're looking at this without applying any voltage, so we consider this a non-biased p-n junction. So it's balanced out right now. But later on, you'll see that when you apply a voltage either in forward bias or reverse bias, you'll see how this p-n junction will react. Either the depletion region will increase or it will decrease depending on the type of biasing you apply.
So there's only pictures right here because it's going to be a pretty long explanation. So bear with me. Basically, at equilibrium, the picture all the way to the left, it's showing what Justin basically just talked about. So he just went over the PN junction, and okay, so we'll just get into it. So you see VA is equal to 0. Basically, that means there's 0 external voltage applied to the PN junction. So when this happens, the semiconductor is at equilibrium. Again, like Justin stated before, P side has majority holes, N side has majority free electrons, and that's going to have a tendency for diffusion. And at the same time, while they're diffusing, there's going to be a depletion region forming in the center. So again, depletion region is going to act as a barrier potential, and that is going to prevent majority carriers from both sides to cross. And that's why you have like that center area. And when that happens, the built-in potential will be present, aka an electric field will exist because of the depletion region. After that, it's going to promote drift, and the concentration gradient will promote diffusion. So these two actions of drift and diffusion are going to cancel each other, thus establishing equilibrium. And as you can see in the picture, because it's at equilibrium, the amount of energy needed to cross from one side to the other, it all cancels out. You can see that only one free electron and one hole is able to cross, but at the same time, it's going to run into the other one that's trying to cross. So it cancels each other out. So the next one that we're going to go over is going to be forward bias. So under forward bias, basically, there's an external voltage applied, and it's going to be positive. So the P side again, the P side is connected to the positive terminal, N side is connected to the negative terminal. And when you do that, when you connect an external voltage in this orientation, it's going to decrease the width of the depletion region. So earlier we were saying that the depletion region created an electric field. So now that we're minimizing the depletion region, what that does is it's going to lower the magnitude of that electric field. So at equilibrium, the electric field was canceling out that diffusion. Well, now that the electric field is going down, it's no longer canceling each other out. So now there will be a current that's going to go across the PN junction. And as you guys can see in the picture, once the depletion region decreases the energy level required for free electrons and holes to cross to the other side, then it'll be easier for current to be present. So again, just shown in the picture, the top 2 layers of free electrons and bottom 2 layers of holes, they have sufficient energy levels to cross to the other side, and they're no longer being canceled out by the other opposing junction. So now we're going to go into reverse bias. And under reverse bias, basically, you do have an external voltage applied. All you're doing is reversing the polarity. So basically, the positive side of the junction is connected to the negative, and the N junction is connected to positive. So what happens in this orientation is the depletion region will actually increase. So when the depletion region increases, the electric field is going to increase as well. And when the electric field increases, then the built-in potential is even larger. So you have even more of a barrier for diffusion to occur. So now it's going to be the opposite, basically. Now diffusion is going to happen less. So at equilibrium, again, it was canceling each other out. Now you have less diffusion. So because of this, there's going to be very, very little current that crosses the PN junction under reverse bias. And because there's very little current, it's going to be referred to as a reverse leakage current. And in the picture, as you can see, now that we have now it's under reverse bias, the energy level required to cross to the other side, it just grew a lot. So now, as you can see, all 3 layers are unable to cross to the other side. But you see that the one free electron in one hole is able to diffuse into the other side. And that's just going to be the reverse leakage current.
All right, so now we're going to talk about what's an ideal diode. So an ideal diode is a diode that acts like a perfect conductor when voltage is applied in forward bias and acts as a perfect insulator when voltage is applied in reverse bias. Meaning that, all right, so if this is forward biased, meaning it can current can flow through, it will act as a closed switch. So current's going to be flowing through infinitely, as we can see here. This is the x-axis is the voltage axis, and the y-axis is the current. So therefore, when the diode is forward biased, it'll conduct current infinitely, while if the diode's in reverse bias, it'll act as an open switch, so no current will flow through. Therefore, it's acting like an open switch. So when positive voltage is applied across the anode to the cathode, the diode conducts forward current infinitely. And when a voltage is applied in reverse bias, the diode conducts no current at all, acting as the switch.
So basically, Justin just went over the ideal diode, but that's just going to be in textbook. It's not realistic at all. Once you go into lab and start messing with these diodes, you're going to notice that there's going to be a difference. So previously, the graph that Justin showed, it was on the x-axis and on the y-axis. Basically, it's a switch like he said, but that's not the case in real life. In real life, we observed in the lab that there's going to be a leakage current when a reverse voltage is applied. So it's not completely on the x-axis. You're going to see that there's a little bit of room, just like Justin's showing right there. And then when a forward current is applied, what's going to happen is that it needs to reach a certain threshold voltage before it starts letting a bunch of current go through the diode. So that's another difference from the real diode compared to the ideal diode. And then another one that we're going to observe is the Zener voltage, or the breakdown voltage. So basically, if you connect a whole bunch of voltage to it, and let's say that the diode is rated at 8 volts, and you go above that, then it's going to either Zener or avalanche, and you're just going to have a bunch of current just go through that diode. It's basically going to just break through it. So that's how I just imagine it. When you apply so much voltage to it, it's just going to break through it, and it's no longer just going to have a small amount of leakage current. It's going to go straight through. And then the last thing that I want to talk about would be the temperature effect. And different from the ideal diode, a real diode, temperature does affect the diode. So if you heat it up, it's actually going to allow even more current to pass through the diode.
All right. So next we're going to be talking about Zener breakdown and avalanche. So kind of like what Kevin said, when you apply a large enough reverse bias voltage on the diode, you'll get Zener breakdown, and this occurs with large amounts of leakage current beginning to flow through due to the depletion region becoming smaller. So it essentially kind of starts to act like if it were in forward bias, but it's not. It's in reverse bias, and the current leaking through is leakage current, but it's a large amount that's going through. So that's Zener breakdown. With avalanching, that occurs when it Zeners. So avalanching is when a charge carrier has enough, well, not enough, it has excess amount of energy to go through the depletion region, which will cause it to bump to another charge carrier. And let's just say that charge carrier didn't have enough energy. But now, since that one charge carrier with excess energy bumps into that one with not enough, that one with not enough is now going to have enough energy to cross through the depletion region, and that one will eventually bump into another charge carrier, which will have the same thing happen. That other charge carrier didn't have enough energy, but now it does, since the one with enough bumped into it. So this will cause an avalanche effect where the ones that have excess amount of energy bump into those without, and they begin to start giving off enough excess energy that they become able to diffuse down the depletion region, causing current to flow through. So we just say that it's avalanching because with an avalanche, if you have like little amount of noise, I guess, you cause a mountain, the snow on the mountain to start coming down with large amounts, and it just wreaks havoc. But yeah, that's basically avalanching. So now we're gonna get into the applications of what diodes can be used for, and we got some pictures to show you. Can you guys see it?
Yes, sir.
All right, cool. So one of the practical applications that we used diodes for is for a full wave rectifier. So with the full wave rectifier, our goal is to have an AC input signal and have a DC output signal. So what these diodes do, I'll explain the whole circuit right now. So we got our AC input, right? And this is a transformer. These coils represent a transformer, and it's center tapped. So when this AC signal goes in, we'll start with the positive portion of it. So this part of the signal. When this signal enters the transformer, it's going to go into this diode right here called D1, and this is what's known as the positive half cycle of of our circuit. So now when the negative portion of our AC signal goes through, it's going to be fed into diode Q, and this diode Q has our negative cycle from here. This is our negative cycle. This is our positive half cycle. Positive half cycle, negative half cycle. So when this flows through, we'll just get a positive 8 DC signal all the way, because this portion comes in through here, boom, gives us that. This negative signal portion comes in through here, goes in through our diode. This is our second wave. So this is called our output DC signal, because normally we would have our load resistor, which will be experiencing our DC output. We'll couple it with a filter capacitor, and what that filter capacitor does is that it decreases the amount of ripple voltage that we'll experience. So think of ripple as like when you have like a little water drop into a pond and you see that little ripple effect. Well, what that capacitor does is it decreases that amount of ripple. So this will start looking more like a straight line the bigger the capacitor you add into your circuit, and it'll flatten out to the point where it looks like a straight line, and that's the DC output signal that you want. So like that, you can be able to use it to charge some of your electronic appliances, like your phone or like your laptop, stuff like that. So the next one we have is our Zener diode application.
So with the Zener diode, what's going to happen here, as you guys can see, there's a sinusoidal input. And then if you check out the output, you're going to see how it just cuts off at the top and on the bottom. So what that's called is, it's called clamping. So we're going to talk about why it's clamping like that. So when you have a sinusoidal input, it's going to go into this circuit, and it's going to come across these two Zener diodes. And they're Zener diodes because you see, like, I guess those little arms that they got. Yeah, those indicate that they're Zener diodes. But when they're facing each other, like how they're facing right now, or even when they're facing away, it could be one or the other. It's going to create this behavior. And basically what happens is it's going to act as a diode protection circuit. So I'm going to use numbers right now to explain it, but we'll say that this particular Zener diode is rated at 8 volts. So what that means is if 8 volts is applied to this Zener diode in reverse bias, then it's going to Zener. So basically, we know that if it's Zener, you're going to have 8 volts. And then in forward bias, diodes are typically, they have a 0.65, would you say 0.6 voltage drop. So when they're oriented like this, either facing each other or facing away, the maximum amount of voltage across the this part is going to be 8.6. You just have 8 plus 0.6. So that's why it's called a diode protection circuit, because as you can see at the output, if we put our load there, that load is only going to receive a maximum of 8.6 volts. And that's why it's getting clamped off right there. And that's one of the applications of a Zener diode. And that's why it's important, because it helps us prevent our load from frying.
And the last application that we have for diodes are LEDs. So these are called light emitting diodes, and they're just basically colorful diodes that light up when you apply a certain amount of voltage, certain amount of current, and you add a resistor in there. So what we would like to have you do is solve for this circuit. So we're gonna say that our battery is rated at 10 volts. Our resistor value is unknown, and our LED has a 2-volt voltage drop when 1 milliamp flows into our circuit. So you can solve this using Ohm's law, and I'll give you guys like 2 minutes to solve this. It shouldn't be that hard. And then we'll go over the, how you would solve it if you weren't able to grab it.
Hey, Justin.
Yeah.
You got like that whiteboard thing where you could write, right?
Yeah.
All right, cool.
Okay. So can you guys see my screen with the whiteboard?
Yeah.
So the way we would solve for this is, all right, we set that it was at 10 volts at our voltage source. We don't know what our resistor value is, and we have this green LED. All right. By the way, these little arrows pointing out of this diode symbolize that it's an LED. So I said that we got a 2-volt drop on our green LED, and that happens when we got 1 milliamp flowing through. So we just use Ohm's law to find out what our resistor value is. So we use R is equal to V over I, and we set this equal to our voltage source. So I'll call this Vs minus that voltage drop on the diode, and we divide it by that current that we have, which is at 1 milliamp. So therefore V10 minus 2 all over 1 milliamp. And does anybody have that calculation ready, or? Because if not, where's my calculator? 10. So you should get about well, that's a lot. 8,000. So that's 8,000 ohms or 8 kilo ohms, whichever you prefer. So therefore, to prevent this circuit, the LED from burning up, you need about 8,000 ohms to keep it from heating up and then burning out. And yeah, that's practically it for that circuit. And
Sounds good.
one way you guys can what's it called, learn more about diodes and stuff is YouTube. Literally, YouTube's a lifesaver. Or you guys can also look up some data sheets too. Like we can search up the 7404. Oh wait, what diodes did we use again, Kevin? Do you remember?
No, I'm trying to. No, I just remember the transistors.
Yeah. Yeah, but you guys can look up the data sheets, or you can go on YouTube, like NISO Academy. NISO Academy has some stuff on diodes. You would just go under analog electronics, and boom, you find everything that we covered here: semiconductor material, intrinsic, electron flow versus hole flow, densities, all this bunch of stuff. And then they go on more into like, all right, well, some configurations where they're in parallel, series. You get the full wave rectifier, introduction to Zener diodes, all that good stuff that you'll learn in 330. And yeah, do we have any questions? I can check the chat. No questions in there. Okay.
Cool.
But yeah, that's all we got for you guys today. I hope we helped.
Well, that's the end of our presentation. If you guys have any advice, recommendations for us to improve our workshops,
Any
let us know right
feedback,
now.
we appreciate it.
Yes, sir. Other than that, you guys have a good day, and thanks for letting us host this workshop.
Thank you. You're welcome.
All right. Well, I guess we'll dip out, huh?
Yeah, I'm gonna stop recording.
Cool, cool.